exercises, it is different. Let us check it. The figure depicts a hockey puck sliding with constant speed v naught in a straight line from point to P. Somewhere from point to P, it is getting slide. From somewhere, maybe point can exist anywhere X. It is sliding to point to P. Point to P, then P to point Q. And the surface is frictionless again. It is an important point to understand. Forces exerted by the air are negligible. So, even clear that instead of applied force, there is no any other force that is disturbing the motion of that hockey puck that is sliding. You're looking down the puck. When the puck reaches point Q, it receives a swift horizontal kick in the direction of the heavy print arrow. As it will reach at this point Q, then it will face a horizontal kick whose direction is represented by this arrow that is shown here, and he is seeing horizontal because it is on the surface of land. It is not in a vertical position. So as a result, he is saying that another force that is directed in the direction of bold arrow is horizontal. Had the puck been at rest at point P, then the kick would have set the puck in horizontal motion with speed Vk in the direction of the kick. So here our first question is which of the path 1 to 5 below would the puck most closely follow after receiving the kick? We need to choose a path from these paths 1, 2, 3, 4, 5, which is perfectly describe the direction of motion of the puck after the kick is being applied. So initially we need to talk about the momentum of the puck when it was at point P. So to the initial momentum we are considering P naught is equal to m. V naught is the velocity they have already told to us, and m is the mass of that puck as it is moving horizontally along the x-axis. So let us place here a unit vector that will represent its x direction. So P naught is equal to m naught E x, that is the position at point P to Q. Now, if they're applying the force to move, then where it will go, that we have to discuss where it will go. Let's suppose it's a momentum from Q that we have to talk. A force F is equal to Fey is applied. About the kick that he is talking is force F is equal to Fey. That is applied at point Q. And as a result, as it is acting at the puck in time delta just like the impulse. And we know change in momentum is actually the product of applied force in a short specific time. So we can write F del T, that is actually the definition of the impulse. And as now the momentum is getting changed after the hit, momentum has become m. Mass of the puck is same, just velocity is getting to be changed, as he is saying that is Vk. So we are representing it as a Vk as it is traveling perpendicular to the initial direction to which we are giving the vertical axis Ey unit vector representing it. So here what we have to do, we need to check the total momentum. Initial momentum is equal to total momentum is equal to initial sum of initial momentum and the momentum gained just after hitting the puck. That is del P, that is actually change in momentum. We need to replace the corresponding value of the momentum, that is m v naught unit vector along the x direction plus m vk unit vector along the y direction. And you can take the common mass, then our relation will become v naught e x to unit vector plus v k e raise head y unit vector. We are actually clearing the component of the velocity because these components will decide the direction of motion of the puck after having a kick. So here finally we have found two component. One is the x component, other is the y component. And if you know about the vector interpretation of something, if you have some vector that is not at some specific axis, so what you need to do, if it is having some angle theta, you need to resolve that vector into its component, x component and y component. If it is vector A, then its horizontal component is x component, ax, and its vertical component is ay. I want to clear that the thing that is necessary for you to resolve a vector is when the vector is not on a specific axis along the x-axis or along the y-axis, it is lying at some angle theta, then you need to resolve it. Okay, so here we are having actually two components that are actually the representing a single vector of the velocity, to which we can say vector v is equal to v naught E x plus v k e y, and it is actually representing the components of some velocity vector, that is v. So component can only be produced of a single vector if it is not lying on a specific axis. So let us check. If we can consider the first direction, then it is normal along the y-axis. It is on a specific axis, so you are unable to resolve at that time to it into its components. So in the second case, you can see it is lying at some angle theta. If it is lying at some angle theta, then you are able to resolve it into its components. And as it is velocity, and we have found its two components, one is a horizontal component v naught and other is a vertical component of vk that we have found. So second direction of motion is satisfying actually our logic that a vector can only be resolved into its component if it is lying some angle, and you are unable to resolve a component if you know its specific direction along the x or y axis. While the other three direction are not possible, how it will turn as the force is in a straight line applied, how it will get such type of slope or the curve shape as the force is applying in the specific direction or such type of curve shape. So other shapes are rejected. The only accepted shape is shape B. Have you understood?
Yes.
Okay, let us check the second part. The speed of punk just after it received the kick. Now you need to find the speed of the punk just as it will receive the kick. What does it mean, speed? You need to actually find the magnitude of the velocity. If velocity is a v, then its magnitude will become v is equal to square root of v naught square plus vk square. That is actually the magnitude of the velocity. In other words, you can say it is actually the speed. So, you need also know that sum of their velocities v naught plus vk is always greater than the square root of these velocities, or you can say its speed v naught square, because it is having a square root vk square, which will reduce its actual value, but that is not our concern. So our purpose was just to show it in its speed, so we have shown its speed. So in the part, it is saying some questions. The speed of the punk just after it received the kick equal to the V naught, uh, it had, just let me change the color. Okay. We have some option from the speed equal to the V naught it had before it received the kick. So if V naught is its initial speed here, and now it is saying that after having a kick, it is having the speed V naught. It is not possible because after having a kick, speed has become Vk. So it is wrong. So the second part, let us check equal to the speed Vk resulting from the kick and independent of the speed V naught. No, it cannot be independent of the speed V naught because V naught is its initial push due to which it is moving from point P to point Q. It is not possible. Equal to the arithmetic sum of the speed V naught and Vq equal to the arithmetic sum. So we have checked here, it is not equal to the arithmetic sum. It is actually greater than the velocity or the speed. In other words, you can say here I can replace V because it is actually the speed. So, fourth, let us discuss smaller than the either of the speed V naught or the Vk as it is sum of two components. So it cannot be smaller than the either speed V naught or Vk. In other words, you can say speed is actually greater than some individual component like V naught, like Vk, or speed, not here, speed greater than Vk. So let us check the last one greater than either of the speed components. So we can agree speed is actually the combination of two components. So individually it will be greater than any single components V naught or Vk, but less than the arithmetic sum of these two speeds, but less than the arithmetic sums of these two speeds. So it is also proved that its speed is actually less than the arithmetic sum of these two speeds. So our conditions are satisfied in the both cases that greater than the either of V naught or Vk. Agreed, but less than the arithmetic sum of the two speeds. Yes, we are agreeing with these two conditions, and option 5 is actually the correct option. Is it clear?
Yes, it's clear.
Okay, let me erase the data to solve the next part. Okay, we have the third part. Along the frictionless path, you have chosen the speed of the punk after receiving the kick. Along the frictionless path, the speed of the punk just after it received the kick is along the frictionless path, you have chosen the speed of the puck after receiving the kick is constant. Speed will be the constant, continuously increase, continuously decrease, increase for a while and decrease thereafter is a constant for a while and decrease after the thereafter. Okay, correct option is A. Why is it is A? Because here we are not applying any external force instead of just a kick. Here the system is having negligible friction because we are talking about the puck moving on a frictionless surface. So energy is not dissipated. The energy it is having, it is moving with the constant speed. It is not dissipated. So its speed will constant. Second option B is continuously increase. How it will continuously increase as we are not providing initial push or any other force instead of just a single kick. So it will not continuously increase. Continuously decrease. It is also not possible because our surface is frictionless. If the energy is not dissipated by the friction, then how it will continuously will be decreased. So it is not possible. Increase for a while and decrease thereafter. As the increase is not possible, decrease is not possible, then how can we say that increase for a while, decrease thereafter? So it is wrong. Is constant for a while and decrease thereafter. It is also wrong. If we think physically, practically is not possible. C, E option can be fine just if we think practically that initially it is having an energy that with which it will move with the constant speed. Finally, on the loss of energy, it will stop or it will decrease. But as we are considering the ideal place where the friction is negligibly zero, there is no loss of the energy. So according to that ideal place, it should move constantly without loss of energy. So option A is correct. Is it clear?
Yes, it's clear.
Okay. And next part 4. Along the frictionless path, you have chosen the main force acting on the puck after receiving the kick R. Okay, on the frictionless path, we need to check which are the main forces. One is the force that we have provided, that is a kick force. But instead of that, we are having some type of the forces or not. Two forces can be possible. One is a gravity that is attracting it towards itself. Other it's the normal reaction of the surface that can balance upward it. So gravity and normal reaction are actually balancing to each other. As a result, it is moving with a constant speed without any loss of the energy. So let us check these options. A downward force of the gravity. If we will talk just about the gravity, then it is actually a violation. How you will balance the force? Normal force. And the next part, downward force of gravity and horizontal force in the direction of motion. These are two forces. But how will you verify gravity as our surface is frictionless in which there is no loss of the energy? If you will consider only the gravity without any other balancing force, then it should stop because of the attraction of the gravity. While it is not stopping, it is moving with the constant speed. So it is not possible. Next one, a downward force of gravity, an upward force exerted by the surface, and a horizontal force in the direction of the motion. Here he is describing the three forces, but just we need only two forces that can balance to each other. A downward force of the gravity and upward force exerted by the surface. That are the only two forces instead of that kick force. So option D is correct here.
Mhm.
Is it clear?
Yes.
Okay. Here we have a question number 3. Which of these systems are isolated? First of all, we need to understand an isolated system is a system in which there is no external interference. That is called an isolated system. So here in these options, he is providing some examples through which we need to check which is actually supporting the isolated system and which is violating the isolating system. In the first part, while sleeping on a patch of ice, a car collide totally inelastically with another car, while our system here in this case is consisting on both the car. So both cars are actually the system. And we are talking that cars are moving and sleeping. If cars are moving and sleeping on the ice, then it can be understood that is there no frictional effect. If there is no frictional effect, there is no loss of the energy, then it can be an example of an isolated system. At the end, I will clear something, but just before that, we need to discuss these points. In the second part, same situation as in a system sleeping car. Here, just you are considering the sleeping car. You are ignoring the second car. If the sleeping car is moving, then it just on its own behalf, then how will you satisfy its collision or its motion? Just we cannot balance here if we are talking about the only sleeping car because it will hit with another car in that system because there are two cars and finally there will be the loss of the energy. A single car slips on patch of ice. Here our system is only the car. Here he is giving actually the complete sentence. A single car slips on a patch of ice. Okay, car is sleeping on the patch of ice, but our system is only car. And if it is sleeping on the patch of the ice, then there is a no loss of the energy, and that car is moving just without the loss of energy because here frictional effect will not exist. Option 4, a car makes an emergency stop on the road. If the car makes emergency stop on the road, you need to understand there will be the creation of the deceleration and some energy will be appeared as a heat energy because of just emergency brakes. So it cannot be an isolated system. A ball drops to earth. A ball drops to earth is its isolated system. It is also not only the isolating system because here ball will move due to the gravity, and in that case it will also face the frictional effect of the atmospheric, for example, like the air. Last one, a billiard ball collide elastically with another billiard ball on the pool table. Both balls. These both balls are actually facing an isolated system because the energy that one ball will have after collision, it will transfer its total energy to another ball, and another ball will move with the same velocity and the same energy. So it is also an isolated system. Okay, but let us wind up this question. If I will say wisely, you can say honestly, none of these system is actually the isolated system.
Mm.
S- Three system, option 1, 3, and 6 are isolated system just for some limits, not totally an isolated system.
Mhm.
Because if we will discuss in this system, some violations can be found, some limitations can be found. So the possible answers that of according to the isolated system are 1, 3, and 6. Is it clear?
Yes, it's clear.
Okay, we have question number 4. A car accelerates from rest. In doing so, absolute value of the car's momentum changes by certain amount and that of the earth changes by. Okay, a car accelerates from rest. In doing so, the absolute value of the car momentum changes by a certain amount, that of the earth changes by. First option is a larger amount. Momentum is equal to the force time over which it acts. The force exerted on the car by the earth are equal and opposite. For example, if car is moving, momentum is actually the product of force applied by the car on the road in time delta. If the car is applying the force on the road or on the earth in time delta, then it will have the momentum. But according to a Newton's second law, in its opposite direction, earth will also apply an other force in the same time, and that will be directed in opposite direction. So both are having actually same momentum but opposite in direction, so they are following the law of conservation of the momentum. Total momentum before and after the pressing of is same. So large amount is not possible because if the core is applying the force on the earth in time delta, in the same time earth is also applying the force on the core in time delta. So there is no increase of momentum because same amount of force is applied here, same velocity is gained by the core as it is applying the force on the earth. So it is not possible for the increase in the momentum by the large amount. Smaller amount in the option 3, if you will say smaller amount, it's mean actually you are violating the law of conservation of the momentum. If you will say car is supplying some type of the momentum to the earth, then as a return earth is providing a little amount of the momentum. How will you justify the law of conservation of the momentum? Law of conservation of momentum will be violated in the part 3, so it is not possible. The answer depends on the interaction between the two. That is not enough answer to explain. So the most suitable answer is the same amount. It is following the law of conservation of the momentum. Is it clear?
Yes, it's clear.
Okay. We have question number 5. Suppose the entire population of the world gathers in one spot. Gathers in one spot. And at the sounding of pre-arranged signal, everyone jumps up. I think 4 to 5 billion is the total population of the earth. And
Mhm.
if you can collect them entirely at the same spot and you want to say that as I will give you the signal, you all need to jump on the earth. Okay.
Yep.
So while all the people are in air, does earth gain momentum in opposite direction? That is the question. that Earth will gain the momentum in opposite direction. So let us discuss its options. While in our previous case, that the thing we have discussed that momentums will always conserved. If you're pressing the earth by your feet, providing some mass and velocity to the earth, in return, earth will also provide you the same thing. Total momentum need to be conserved. So let us check. In the first part, no, the inertial mass of the Earth is so large that the planet's change in motion is imperceptible. He is justifying just the answer as the mass of the Earth as compared to the mass of that population is more larger, so it will not affect. But it is not the answer because it is violating the law of conservation of the momentum. Second part, yes, because of its much larger inertial mass. However, the change in momentum of the earth is much less than that of the jumping people. Again, it is violating the law of conservation. If the jumping people are providing some type of the momentum, in return, earth will also provide the same type of the momentum in case of the recoil. So, if Earth will provide the same type of momentum, then total momentum will be conserved just before and after hitting the Earth. So, it will be actually law of conservation. So, option B or the second option is not possible. Let us check third option. Yes, Earth recoil like a rifle firing a bullet. When you fire a bullet by using the rifle, as the bullet move forward and then rifle move backward in opposite direction. And as the bullet is having high speed but low mass, but the product of mass and speed is constant, while the rifle is having heavier mass but low speed, but again the product of mass and velocity will be the constant. If the bullet is having high speed but it is having the low mass, that is compensated by the heavier mass of the gun just with the slow speed of the recoil. So that is also the case of action reaction and conservation of the momentum. So he is just actually satisfying you and the law of conservation of by giving an example of the bullet fire from the gun. Just similar as you will jump on the earth, you will provide or transfer the momentum to the earth. In the return, earth will also provide the same momentum to you. The biggest proof of it is that as you jump on the earth, then as a return, there is no change. Why is no change? Because the momentum that you have supplied that is returned to you, net momentum is equal to zero. As a result, there is no change. Okay. So, third or fourth option, it depends. Uh, it depends. Okay, that is the only thing I was thinking that something is below. Okay, it depends. It depends on the situation, but it is not enough information to decide that statement is correct or not. Okay, fine. So here we have question number 6. Suppose the entire population of the world, again the same thing, gather in the one spot and the sound of the pre-arranged signal, everyone jumps up about a second later, 5 billion people land back on the earth. After the people have landed, Earth's momentum is, what will be the Earth's momentum? Same as what it was before the people jumped. We need not to discuss or utilize time on it more
Yes.
because we have discussed its momentum will not change, it will remain the same. Okay, so first option. Okay, here we have question number 7. In the 7, what you can see, there is a card, and above the card, raindrops are falling on the card while cart is moving in this direction. And these raindrops are falling on it downward and filling the water in the space of the card as shown in the diagram. Okay, suppose the rain falls vertically into an open card ruling along a straight horizontal track with negligible friction. As a result of the accumulating water, the speed of the car increase does not change, decrease. So, first of all, our system is negligible friction. Here, there is no interference of the friction first thing. As the cart is moving forward, while the raindrop are moving downward vertically, these raindrops are actually not disturbing the direction of motion or the x component of the motion of this cart. So, due to this fall of these raindrops, it will not affect. Yes, something is other can affect that as the water is accumulating in it, and it is actually increasing its mass. If its mass or the weight will increase, then automatically you need to understand its speed will be reduced. So option 3 is correct. Speed will be reduced. Yes. Is it clear?
Yes, it's clear.
Okay. Question 8, same scenario. Suppose rain falls vertically into an open cart rolling along the straight horizontal track with a negligible friction. As a result of accumulation of the water, the kinetic energy of the cart. What will be done with the kinetic energy? If shortly I will say, as the speed is reducing, we know relation for the kinetic energy is equal to half mv square. If the speed is getting reduced, then it is understood kinetic energy should be reduced. Option can be 3, but we need to discuss it because in here, suppose the rain vertically occur horizontal track and negligible friction result of the accumulating water, the kinetic energy of the cart will be reduced. Okay, we can rewrite this kinetic energy as V by 2 dot mv. I want to show that momentum is actually constant. Constant. If the momentum is constant, the factor of velocity that is getting decreased is just v by 2 here. It will be decreased. So since momentum mv is conserved, so only v by 2 changes with the flow of the time, which is making this collision inelastic. So, as the dissipation of the energy, kinetic energy, because of the reduce in the speed, because of the increase in the weight due to the water, due to the rain droplets, energy loss is showing that it is not actually the elastic collision. In elastic collision, momentum and kinetic energy both should be conserved. But here, speed is reducing, kinetic energy is reducing. As a result, it is not an elastic collision, it is inelastic collision, just because of this small reduce in speed. Okay, this loss of the energy can be appear some type of the heat because as the weight will be increased due to the increase in the weight, then the pressing force of the tire on the road will increase. As a result, their contact will increase, and somewhere due to a little bit frictional effect, if they are saying that we need to ignore, that can be possible. Practically, if we need to think, there will be loss of energy and appeared as a heat energy.